Welcome everyone to the fourth lecture of the GR course. In the past few lectures, we have developed some machineries to study covariant derivatives, and we always said that our main motivation for studying covariant derivatives is that we want to understand the local structure of a manifold. And by that, we really mainly mean the curvature structure of a manifold. Um, So we kind of motivated the introduction of a covariant derivative using pictures such as the one that I'm going to draw right now. So let's say, so I think I drew something like this, and then there were curves that form a loop, and we kind of said that we should be able to detect what's going on locally in a manifold by parallelly transporting vectors around closed curves, and then comparing what we find at the end of these paths. Um, and we introduced the covariant derivative as a way to define the parallel transfer. So today we are going to put these machineries in practice, and we are actually going to concretely define and compute curvature for an arbitrary manifold given a metric. Okay. So let's try to make these kind of pictures that we have been drawing more precise. So what we want to do is that um, so we want to start at some point of our manifold, and suppose that in our manifold we have two vector fields. Uh, just let me choose this. Right. So this is going to be our starting point. Let's call it x. So by x, I really mean that there are a bunch of coordinates, right? So x1, x2, x3, x4, etc. And then this is going to be a vector u. So we are going to think of u as really a vector field, so that there's a vector u at every point, really. So something like this. So it's a vector field, okay? Uh, but I am really going to draw just this one located at x. And so recall that starting from any point on a manifold, a vector defines an infinitesimal displacement of the point. So the point where we end up at the end of that vector. So you can think of this as being a point that's very close to x, separated by a vector u. Okay. Similarly, we have another vector field v pointing to some other direction, and this point is going to be x plus v. Okay. I should really write u of x, because as they're saying that this vector is located at x, and we have the same vector at other points. So this u of x is really, I'm referring to this vector. Okay. And so this, I'm going to say that this is ux plus v. So it's the same vector field, but evaluated at a different point. So it's evaluated at x plus v. And similarly, this will be vx plus u. So it's the same vector field as v, but located at a neighboring point as opposed to x. Instead of x, you look at x plus u. So there's the question, the geodesic equation that we derived last time, was it for 2D or 3D? Because the geodesic equation that we derived has some extra terms as compared to the one I did before. So the geodesic equations are independent of dimension. They should be the same in all dimensions. There shouldn't be any difference in the geodesic equation. There may be some difference depending on the parameter that you're using to parameterize your curve. Because the geodesic equation is that the covariant derivative of the tangent to your curve is proportional to the tangent itself, but the proportionality constant will depend on the parameter. So if that is the difference, then there may be a difference, but it doesn't have anything to do with the dimension, but rather the parameter itself. Okay, so back to our setup. So starting from a point x, and given two vector fields u and v, we have defined some neighboring points of x. So you can first either follow u, then follow v, or you can first follow v and then follow u. Now, in general, you will not end up at the same place, right? So you will end up at different places. And we are going to quantify this difference as well. But for now, let me say that we will always close this gap by whatever is necessary. So let's call this difference delta. Okay? So let's see what delta is. Um, so what is this point, for example? This point is simply x plus u plus v evaluated at x plus u, right? And then we can use Taylor series. So this is going to be x plus u plus v plus u mu del mu v. Okay. Someone is saying that my screen is not showing. Is that true for everyone? Can you see my screen or no?
I think the screen is visible. Maybe try rejoining the Zoom again.
Are you referring to me or the person?
Sorry, you. Sorry. Yeah, your screen is visible to me,
Okay,
and in the chat other people can see it as well. So maybe it's a personal.
I see. Okay, great. All right. Um, so yeah, I was talking about what this point is. So this point is that you start at x, then you add the vector u, and then you add the vector v, but it's v located at x plus u, right? So it's x plus u, and then v located at x plus u. And so once more, so I should really write u of x, but since I have to write of x a bunch of times, I will simply omit the of x. So whenever I write just a vector field without any argument, it will be understood to be located at x. Okay. So for example, here, this vector field as evaluated at x plus u. That's why I'm explicitly writing x plus u. But then if I Taylor expand, then this is going to be v of x, and I am omitting that of x. Okay, so in the Taylor series, we have more terms involving higher order derivatives. We'll get quadratic and so on and so forth. But since this point is infinitesimally close to x, we can ignore higher than the linear order terms. So there's a question, does x, u, and v have the same dimensions? Yes, of course. So x, let's say that we are in d-dimensional manifold. So then x means x1, x2, dot, 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 xd. And similarly, u means u1, u2, dot, dot, ud, and so on and so forth. And I'm going to write these when I'm writing the indices, I'm going to write them as u, mu, and so on and so forth. All right. So this vector, or really this point, represents a point infinitesimally close to x that you find by traversing this path. So now let's see what happens if we do this. It's very similar. So it's going to be x plus, actually, we don't have to compute again because the difference between this and this is simply which one you followed first, right? So if you swap u with v, you should find the expression for this path. So it's going to be x plus v plus u plus v mu derivative with respect to u. Okay, all right. Uh, As you can clearly see, these 2 points are not the same. So these parts are the same. So these cancel with this with this, and this with this. But these two terms are different, um, which is why you have this non-zero gap between these 2 points. So the previous question where someone asked that whether x, u, and v have the same dimension, the answer again is yes. They have the same dimension. They have the dimension of distance. Okay. So what is the difference? So as you can clearly see, um, that in order to go from here to here, in other words, from here to here, we have to subtract this and add this. So we can say that delta is going to be minus v mu del mu u plus u mu del mu v. Okay. And all of these are vectors, obviously. So I can put indices if I want. All right. So the point is that if you add this and this, you end up with this. Meaning to this path, you add this delta, and then you end up at the same point as this path. Okay, very well. So this is going to be the loop around which we are going to transport our vector and see what we end up with. So basically what we're going to do is that we are going to introduce another vector field. Now let's call it W. So we will start from, let's say something like this. So some vector field W. And then first we're going to parallel transport this W along this path. So then there will be W here. So W at x plus u. And then we will parallel transport this to here. So W x plus u plus, okay, this thing, this V of x plus u. And then we are going to parallel transport the same vector around this path. So there will be some W here, x plus v, and then a W here, x plus v plus dot dot. Then we have to further transport this somewhere here. Let's say, so this is going to be wx plus v plus ux plus v plus delta. And what we're really interested in is the difference between them, right? So this difference is what will tell us whether there is non-zero curvature in this region. So if this space is flat, then this would be zero, meaning regardless of which path we take to do the parallel transport, we will end up with the same vector. If this difference turns out to be non-zero, then that difference will give us a measure of curvature inside this space. All right. So now let's get on with the computation of what we find if we parallel transport this along this path and along this path. For future reference, let me give some names to the points. Maybe I can say this is P, this is Q. So this was P, this was Q. And this was P minus Q. Okay. So far, so good. Now let's see what we get by doing the parallel transfer. So first of all, we're going to expand these using Taylor series. So any vector field, so W Then I put the index mu x plus u. This we can always expand using Taylor series. And so what you're going to find is W mu of x, which I'm going to ignore, plus u mu first derivative W, right? Uh, that index, right? New, new, new. All right. Um, okay. Now, so this is true for any vector field. So how do we impose the constraint that W is being parallel transported from here to here? Mm, So here you have to recall the definition of parallel transport. I hope you guys remember the definition of parallel transport from previous lectures. Um, so the definition was simply that um, W is parallel transported along U. This means that the covariant derivative of W with respect to U vanishes. All right. Okay. And what was our expression for the covariant derivative? So this implied that so the covariant derivative, recall that it starts with the partial derivative, and then you have a term involving the Christoffel symbol, right? So this was the condition satisfied by W if it is being parallel transported from x to x plus u. Now, for any W, its value at x plus u can be written like this. And again, just to be clear, so there are terms of higher orders in U square, but we're going to ignore them because we are infinitesimally close, so U is small. Uh, now, if W is parallel, then we can replace this partial derivative with respect to the Christoffel symbol, right? Using this equation. So what that means is that W is parallel along U. This means W mu x plus U is equal to W mu minus this. So here, all we have done is that we have replaced this using this equation by the negative of this term, right? And that's it. So there is one question. Can we just take the equality of the equations for geodesics and shortest distance to measure the curvature with the extra term in the geodesic equation? Can we just take the equality of the equations? So I did not fully understand the question. Can you elaborate a bit more? There's another question. Does this transportation along a curve or a straight path or a path that obeys the geodesic equation? Okay, that's a good question. So this transportation is happening along the direction of a vector. So it's neither necessarily straight nor a shortest path. It's a completely arbitrary path. Because the statement that we want to end up with is that curvature can be detected by uh, taking a vector and parallelly transporting it in different ways along any arbitrarily chosen paths. And if they differ at the end of the two paths, then you have a non-zero curvature. So the paths can be completely arbitrary. There is no constraint on the paths whatsoever. It's just a direction determined by this vector field. That's it. Yeah, there was one question that I didn't fully understand, which was that can we just take the equality of the equations for geodesics and shortest distance to measure the curvature with the extra term in the geodesic equation? I'm not sure what the extra term refers to, but I mean, we are going to use the geodesic equation to derive the formula for the curvature. Well, sorry. Actually, we're not going to use anything about geodesics. As I was saying, that these paths are completely arbitrary. They're not geodesics. Okay, so let us move on. So we have found the expression for W at this point when it has been parallelly transported from X. So we can follow this procedure and transport this parallelly to this point. Um, so what we're going to do is that just repeat this process, right? So here you have W, and here you found an expression for the parallelly transported vector. So now you start with this, and instead of transporting things along U, you transport things along Vx plus U, and then you will find an expression for this vector. All right, so let's see what that is. Um, it's going to be, so the first term is what you already have, like this, right? So we started with W, so you have W. Now we're starting from this, so we have this. And then there's going to be a term involving the Christoffel symbol. But before I write that down, let me start with an earlier expression, which is just the partial derivative, right? Okay, it's going to look like this. Okay, so notice what this is. Mm, So this expression, which is true for any vector field. So you simply have W at X and the vector along which you're transporting things, partial derivative, and the original vector. All right. So notice the same structure. So this is the vector that we're transporting. This is the vector that determines the direction in which we are transporting. And here you have to put x plus u because we are moving from here to here. So the vector here is vx plus u. Then you have a partial derivative, and then the original vector. It's the same as this. Okay. And as I was saying, that this is true for any vector field, but if the vector field is being parallelly transported, then you can replace this partial derivative by the action of the Christoffel symbol. So let's do that. So this equality only holds when things are parallel. The only thing that you have to be careful about here is that the Christoffel symbol also have to be evaluated at the same point as your source. So here, right? So at x plus u, and that's it. Um, Now, so once again, we are going to replace all functional dependence, such as this x plus u, by using Taylor series and keeping terms that are linear in the Taylor series. So what you will find at the end of the day is, actually, I'm going to simplify even a bit further. So notice that if I expand things that are up to linear order in U here, up to linear order in U here, then after taking products, we are going to find some terms that are cubic in the vector fields. So for example, take the linear term from here and the linear term from here, and then if you multiply with this, then you're going to find three factors of u's, okay? Um, and we're going to ignore all such terms. We're only going to keep terms out of all of these that are at most quadratic in the vector fields. So ignore terms of order, say u square v, v square u, or higher. Now, what is the justification for this? This is actually being done with some foresight. So what I mean by that is that I know what I'm going to find at the end of the computation, so I'm using that knowledge to some extent. Because what I will find is that once I parallel transport these vectors along two different paths and then compute the difference, so there would be no difference between those two vectors at linear order in these vector fields u and v. Okay. And the first non-zero difference will arise at the quadratic order. So that quadratic order means u squared or v squared or uv. Okay. And it's that leading order difference between the two uh, transported vectors that we are interested in. Because at the end of the day, we are going to take the limit that um, this loop uh, is, it becomes basically of zero area. When this area essentially becomes zero, and then we find some expression that's truly local. So we only need the leading non-zero behavior. If it turned out that the first non-zero difference comes in order uh, u cube or something like that, then we would keep up to that order. But since I already know that that's not going to happen, I'm simplifying computations by killing terms of this order. All right. So doing this, what we find is that this is equal to um, one problem with this kind of expressions is that you end up with so many indices, you kind of start to run out of letters. Okay. It's a long expression. I hope I have it right. It's a long expression, but it's a very easy expression. So these terms are as they are, nothing has changed. Then you expand these in Taylor series. So from there, mm, so you expand these in Taylor series, and then so you multiply all of these terms. So there is going to be one term which is this at x, this at x, and this w. So that's this term. And then similarly, you get a term where this is evaluated at x, this is evaluated at x, these two, and then you have this term, and so on and so forth, right? So then you have a term where we have a derivative of this, and we have a term where we have a derivative of this from the leading terms in the Taylor expansion. So those are these and this. Okay. And again, recall that there are terms of higher orders, like u squared, v squared, sorry, u cube, v cube, and we are ignoring all of those things. Okay. So this expression gives us this vector. All right. Now we have to do the same thing, but now we take this path. And it's almost the same. So these first two steps, it's basically the same. We just replace v and u. I mean, you swap v and u. But then we have to do an extra step because of this delta. So let's do all the steps. So, okay, as I was saying, that the first two steps, so going from here and then here, is identical to going from here and then here. So here we followed u and then v. Here we just have v and then u. So take this expression, but swap u and v, right? And just to keep track of things, this is our w mu at, what was the name of the point? P, here. This is W mu at P, but we also have to remember which path we took, right? So let me introduce a different notation. Let me use T for transport. So we transported first along U and then V. Okay. So I'm going to call this U and then V. All right. And now we need to compute, let's say, first we need to compute first V and then U, W mu. And if we do this, we will end up at Q. So you do first V and then you do U, and then you will end up at Q. This expression is nothing but this, where you swap U and V. So let's do that. Wherever I have U, I will put V, and wherever I have U, I will put U. All right, so that was easy. But we have one more step. Well, let's see if there are some questions. In the index of the Christoffel symbol, is that X or chi? It's chi. So for all the indices, I'm using Greek letters. How can we determine all the components of Christoffel symbols and what will be our constraints? Can you please explain why we can't end up on the same spot from where we started? Okay, so let's address the first question. So how can we determine all the components of Christoffel symbols? Well, we have to know the metric, and then there's a formula for the Christoffel symbol in terms of the metric that we wrote down in an earlier class. And we are going to see some of that in some of the problems that we're going to work out later on. And can you please explain why we can't end up on the same spot? Well, that's easy. So, so as I was saying, so what is P? So P is you start at X, then you first add U, and then you add V evaluated at X plus U, right? So if you do that, you find this expression, X plus U plus V, and then derivative of V with respect to U. If you do the other way, so first V and then U, so now V is just V, but you're evaluating U at X plus V. So you have X plus V plus U, and then derivative of U with respect to V. I mean, just by looking at these two expressions, you can see that they're not the same. These parts are the same, but these parts are different. So you can compute what the difference is, and you find something non-zero. That's why you don't end up at the same place. It's really because U and V are completely arbitrary vector fields, as we said at the beginning. All right. Covariant derivatives do not commute. That's true, but so notice that that's in this case, that's not the reason why you don't end up at the same place. I mean, even if covariant derivatives commute, you would still not end up at the same place for two arbitrary vector fields. It's just because they're arbitrary vector fields. There is a condition for which you will end up at the same place, and we will use that condition later. So you will see more explicitly perhaps then. Um, if we choose two different paths to P and Q, would delta be the same? Yes, delta will be the same. Delta only depends on P and Q, right? It's the difference between P and Q. It doesn't depend on how you ended up at P and Q. All right. Okay, so now we are at Q and we need to end up at P. So we need to add delta. We need to transport these further a little bit by delta. So how do we do that? So we have been transporting vectors so far, right? And we already know how to do that. That is that you simply take the vector that you want to transport, and then you add a derivative with respect to the vector in whose direction you want to transport more. So for example, so here we are transporting W from X to X plus U. So we take the vector that we originally have at X, and then we take derivative of that with respect to the vector that determines the transport. Now, looking at this, it seems a bit messy, right? So because what we really have to do is that we have to take this, and then we have to take delta, what is the next Greek letter? Honestly, I don't know. Let's call it alpha. Then alpha, and then we have to take this thing and put it here, right? It looks a bit messy. But we don't actually need to keep track of all these terms. Because what is delta? So delta is this expression. It is already quadratic in the vector fields, right? And as we said earlier, we're only keeping tracks of terms that are at most quadratic in the vector fields. So this is already quadratic. Quadratic in UV. And since this is the highest order up to which we are keeping track of the terms, we only need to keep track of terms here that have absolutely no dependence on U and V, right? And so here, how many terms do we have that have no dependence on U and V? So here you have V, U, 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 V, V, U. So all of these terms, if we put them here, they will be of an order that we're ignoring. So this is the only term that we need to put in here. So this is basically the only thing that we care about. Uh, so let's do that. So we take this, we add this, and we end up with T, first V, then U, and then delta, W mu, and we are back at P along a different path. So what is this expression? This is nothing but this. And then just add this, where substitute for delta, this expression that we have. This is easy enough. All right. So we have our two expressions that we want to compare. We have the expression of W mu at P when we arrive at P via this path. First V, then U, and then delta. Uh, this path, sorry, this path. And we also have the expression of W at P when we simply took first U and then V. So that's this path. And this difference that we wanted to compute, it's going to be the difference between this expression and this expression. Yeah, it looks a bit big, so you may think it's going to be messy, but really well, not many, but some of the terms will cancel out, okay? So the difference that we are interested in is right. So right now, I don't really expect that you can just look at this thing and remember all of the terms and figure out which terms cancel. So let me just point out some of the terms, and you can carefully look at this computation later. Um, Actually, maybe it would be easier if they were side by side. So let me do that. I'm just going to copy this expression. So all we have to do is compare these two things. So you immediately notice that they will cancel. This will cancel. This will also cancel. Notice that in order to cancel this, we have to use symmetry of the Christoffel symbol with respect to these two indices. So that's torsion-free stuff. Um, and if you look carefully, and because for now, just you have to believe me that nothing else will cancel. So all of the remaining terms will survive. Um, but that's okay because all of those terms will have interesting interpretations. So let me first write down what those terms are, and then I will interpret as to what those terms mean. I will do some simplification and not write all of the steps. Okay. So one thing that may seem a bit surprising is the appearance of this covariant derivative, because in these expressions, we didn't have any covariant derivatives. However, notice that mm, these four terms, so here you have this vector, which is the same as this vector. But here you have a partial derivative, and here you have a Stoffel symbol. So when you subtract this from this, they will have the same sign, and you can take this as a common factor, and what you will be left with is a partial derivative plus a Christoffel symbol, which will combine to give you a covariant derivative. And the same thing will happen for this and this. So in that way, you end up with these expressions. Okay, so this is it. So this is the difference between the two vectors that we find after we parallelly transport W from X to P along two different paths. So this expression is this vector, the difference. All right. So that means that on a flat space, we would expect these to vanish. Now, that's not entirely true because of this term. Because suppose we are on a flat space. So what happens on a flat space is that there is no non-trivial Christoffel symbol, right? So the partial derivative is covariant. Uh, so all of these terms will vanish because they depend on the Christoffel symbol. And there's Christoffel symbol inside of this as well, um, which will also vanish, but it will still have the partial derivatives. Okay. Silly. It's the same derivative, so I don't have to write it twice. All right. But this term, there is no reason why they would vanish, right? Even on a flat space. It's just partial derivative of some vector field and partial derivative of some vector field, and there's a difference. So the point is that if you take two completely arbitrary vector fields u and v, and then you do this parallel transport, then even on flat space, these two vectors that we end up with will not be the same. There will be a difference. But this difference is not caused on flat space. It would not be caused by the local curvature of the space, but rather this difference contains some information about how these two vector fields u and v behave. So this is a property entirely. So this is a property entirely of this u and v. This does not tell you anything about the local structure of a manifold. And this factor, this has a name which on a slightly longer course we would have had time to discuss, but as it stands, we don't. But this is called a Lie bracket or a Lie derivative of vector field with respect to another. So you will often, in textbooks, you will see terms like this. So two vector fields v and u, and some kind of bracket like this. And so this expression is nothing but this. So the point is, so given any two vector field, we can define another vector field by applying certain operation that looks like this and is usually written like this, and it's called the Lie bracket of vector fields. And this is something to do with the vector fields themselves. About how a vector field changes uh, when you follow the flow of another vector field and so on, and they can express certain symmetry properties of manifolds. We may make some comments on that later. But for now, just try to convince yourself that this term really has nothing to do with the local curvature of a space, and really it's a property of the two vector fields. And you can choose these two vector fields. Well, if you choose these vector fields to be such that this vanishes, for example, you can choose u to be just a coordinate vector field. So if let's say you're in Cartesian coordinate x, y, z, etc., etc. So then u can just be del x, right? So what that means is that you have x, y, z. So you can take these as one of the vector fields, u, right? So in that case, the partial derivative of that with respect to any other vector field, or really any vector field, is going to vanish, right? Because it's just a constant. You would write it as 1, 0, comma, 0, comma, 0, so on and so forth. So you can make this vanish by choosing u and v carefully. So then what you will be left with is this. And this is the term that you cannot make zero, regardless of what your choice of u and v are, if this happens to be non-zero. So what we learn from this is that this is the expression that should really tell us about the local curvature of our spacetime. So this is the thing that we are going to define. So we're going to give this the name of a curvature tensor. So you have to figure out what the free indices are here, right? So nu, sigma, which are contracted with these things, and mu, which is not contracted with anything. It's a free index. And tau, which is contracted with this outside. So chi is contracted here. Chi is contracted here. All right. So these are the free indices in this expression. So you define a tensor which has 4 indices, and you call this your curvature tensor. It's called Riemann curvature tensor. Okay. And the Riemann curvature tensor looks like this in terms of your Christoffel symbols. And the Christoffel symbols themselves can be written in terms of the metric. So basically, the Riemann curvature tensor itself has an expression in terms of the metric and nothing else. It will look a bit messy because there will be a bunch of terms. Okay, so before we move on with more properties of the curvature tensor, let's see if there are some questions. Okay, there are several questions, so okay, I will take some time to answer them if I can. If Christoffel symbol needs to be evaluated as different places, does that mean our covariant derivative operator itself is changing? Yes, the covariant derivative depends on where you're taking the derivative because the Christoffel symbol depends on the location on your spacetime. If we choose two different paths to P and Q, would delta be the same? Yes. Oh, I think I already answered that. Is it necessary to take the Taylor expansion? Why? Well, it's because um, we really want to know the local geometry around this point X, which is why we are expressing all of the vectors that we have at different points in terms of its values and derivatives evaluated at X, right? So that's what Taylor expansion allows you to do. It allows you to write the value of a function or a tensor at some point in terms of the value of that function and its derivatives at a different point. So we are expressing all of these things in terms of the values and derivatives evaluated at X, so that when we end up with an expression of our Riemann tensor, such as this, so everything that you see in this expression, so the value of these Christoffel symbols or the derivatives of these Christoffel symbols, they are all evaluated at X. So that expression of the Riemann tensor, it is defined at this point. You don't need to know anything about what's going on away from this point. I mean, you need to know the value of things in an infinitesimal neighborhood of this point so that you can take derivative. I mean, so derivative has information about a small neighborhood of a point. That's all you need to know. Which is why we can say that yes, the Riemann tensor is a local quantity up to dependence on derivatives that depends on what's going on at X. So it's a Riemann tensor. So the Riemann tensor that we define is a Riemann tensor here. Okay? I mean, we utilized a path that kind of goes away a bit. It's still infinitesimally close, but it goes away a bit. But notice that now all the information about the path is outside of the definition of the Riemann tensor, inside this U and V, right? The U and V dictated which paths we took. But the Riemann tensor itself, it only depends on the local point X and derivatives there. Okay, so if there was another path to P, say x plus a plus b x plus a, would we reach Q if we do x plus b plus ax plus b? Okay, I need to know what it means. If there was another path to P, so x plus a b x plus a. Oh, no, so you would not necessarily reach Q if A and B are different. You would reach some other point. Which point you reach depends on which vector fields you take. So do X, U, and V belong to the same tangent space? So X is a point in your spacetime. U and V belong to the tangent spaces. So in pictures, it looks something like this. So suppose this is your manifold. So you have a point X, and then so from X, you can go to different directions, right? So let's say this is U and this is V. So from X, you move away a bit using U or V, and so on and so forth. So can you tell us the relation between Lie bracket and Poisson bracket and their significance in classical theories? That is a very nice topic, but unfortunately, we do not have time to talk about it right now because we still have some stuff about the curvature to cover. Um, but you will find them in textbooks, and okay, I will try to refer you to some books at the end of the talk. Lie bracket looks like curve. Not really. It's not curved. It's different. I mean, it's antisymmetric in the two vector fields, but it's not curved. So curved is something that you can only define in two dimensions. It's a very specific thing. Lie bracket is a much more general idea. So Poisson brackets are defined in phase space mainly. Yes. Lie brackets are operation on any manifolds. Yes. As far as I know, we use symplectic manifolds while studying phase spaces. That's true. Symplectic manifolds require non-degenerate two forms. That's right. The Riemann curvature tensor from Carroll, section 3.6, defines an infinitesimal loop defined by two vectors A mu and B nu. So more additional constraints are for Poisson brackets. Um, yeah, that is correct. So in order to define Poisson brackets, you need more structures, like a Poisson manifold that has a Poisson structure. Okay, that's it. Good. So now we have defined a quantity with four indices, and we have kind of argued that this quantity knows about the local curvature of your spacetime to the extent that it can dictate how a vector transported along two different paths differ at the end of their transport. So in other words, notice what we did. So we computed this vector, right? And so this vector, so we computed as a difference between this vector and this vector, where we found them by following these two paths. So basically, if you take this and subtract this, it's the same as saying that you do this and then add the opposite path, right? So the vector that we computed is really what you get by parallelly transporting this vector along this closed path and coming back. And then you see that it doesn't quite come back to itself, but it differs by a vector. That's what we really computed. And this difference is governed by, well, we saw that it is governed by two quantities. One is this, that depends only on the structure of a manifold. And the other is this, which depends on the two vectors that are used to define this closed path. So we declared that, okay, this is a property of the vector fields that we chose and has nothing to do with the local structure of the manifold itself. And this is the local structure of the manifold that governs this parallel transport. So we call this curvature and we call this something else that has to do with vector fields. All right. Um, one more question. So we don't need metric to compute the Lie brackets, right? Yes, that is correct. You don't need metric because it is not about the manifold, but about the vector fields. So now let us look at some of the properties of this Riemann tensor that we have defined. So properties of Riemann tensors. So first property, what it says is that if you swap these two indices, you get a minus sign, which is, so forgot to mention something very important, which is that Riemann tensor has another expression, which is much simpler. And it looks like the following. And this is also sometimes written as this. All right. And so how do you prove this? Well, you have your formula for the covariant derivative. Just plug it in, and you will observe that you end up with this expression. Okay. So this is this. You can show that by explicit computation. However, something that this makes obvious is that this expression is antisymmetric in mu and nu, right? So if you swap mu and nu, you will get a minus sign. Another property. So you cyclically permute these indices. So mu nu rho, nu rho mu, and rho mu nu. And if you add these things, you will get 0. So I am actually not going to prove these formulas. So there are a few more. I'm not going to prove them because they're part of the standard textbook. You can look at Wald or Carroll's book for these formulas. Maybe I can tell you which section. Let me see. Well, so you will find proofs of this in any GR textbook. So in particular, you can look at World section 3.2. Yeah, so this is the reference for these identities that I'm writing down. But again, you will find them in any textbook. It's just this book is open on my computer right now. Another identity. So actually, let me introduce a notation. This same equation, you will see it also written as follows. Okay. So what this means is that it means anti-symmetrization with respect to these indices. So it literally means you write down all of the permutations of these indices. So there are three, so there are six permutations. So it's going to be, say, mu new row, mu row new, and okay, there are four more. And then for each odd permutation, you put a minus sign, and even permutation plus sign. So what does even and odd mean? Okay. So it means how many transmutations you have to do. Or okay, so roughly speaking, so how do you go from here to here? You swap new and row, right? So then you get this. So the number of swaps is one. So you can say that if the number of swaps is odd, it's an odd permutation. If the number of swaps is even, it's an even permutation. So that's it. So it's just that you take all of the permutations of this and you put signs based on whether it's an odd or even permutation. And you sum that up, and that has to be zero. That's all that this means. So how does it become three terms instead of six? Well, using this antisymmetry, you can add some of those terms. So two of those terms will add up to become one term because of this. And then you will find this expression. And the reason that I am introducing this notation is that the next formula is most easily written as follows. So now there's a covariant derivative of the curvature tensor, and again, you antisymmetrize these three indices. And the last formula that I'm going to write down is actually, this is slightly more complicated than this one, so let me put it at the end. So what's going on here is that similar to the first two indices, which are the same here, so I am swapping the last two indices, and it's again antisymmetric with respect to the last two indices. That's it. Okay. So right now it may seem like this is some random formula satisfied by the Riemann tensor. Who cares, right? But it turns out that these formulas are quite useful when you're doing computations, because as you can imagine, that there are many components of the Riemann tensor, right? So it has four indices, and let's say in four-dimensional space, each index can take four different values. So this tensor has 4 to the power 4 components. And in D dimension, it has D to the power 4 components, which can be a very large number. So even in 4 dimensional, what is 4 to the power 4? I'm not sure. It's a very large number. So the point is that all of these components are not independent. Many of these components are related to each other by these symmetries. Which is why this is helpful to simplify many computations. Let's see. Okay. Now, as I was saying, the Riemann tensor has four indices and many components. We can define something that has some of the information of the Riemann tensor. So it has some curvature information, but maybe not all of them, by contracting some of the indices. And those tensors that we will find after contractions, they also have interesting properties. So it's worthwhile to define them. So let us define uh, the so-called Ricci tensor and scalar curvature. The definitions are extremely simple. Once we have the Riemann tensor, so for the Ricci tensor, it is defined as follows. So it's a tensor with two indices that you find simply by contracting two of the indices of the Riemann tensor. Okay, so you contract one of the middle index and the last index, and you're left with two. Well, so you can ask, so why these two and not some other two? Well, so notice that because of the antisymmetry between the first two indices, it doesn't matter whether we contract this with the middle one or the first one, right? It's the same, basically, up to a sign, which is a matter of convention anyway. And you couldn't really contract this with this because this tensor is antisymmetric when you swap the last two indices. So if you multiply this with rho sigma and multiply this with rho sigma, or multiply this with rho sigma, which is how you contract two indices, right? So I'm raising the last index basically. Uh, so the tensor, the metric tensor is symmetric, and if you contract it with two antisymmetric tensors, you're going to get zero. So the point is, if you contracted this with this, you would get zero. If you contract this with this, you would get basically the same thing as this up to a sign, which is a convention. So this is basically the only thing that you can define. That's non-zero. And the scalar curvature is when you further contract the remaining indices. So you take the two indices of the Ricci tensor and you contract both of them, and what you get is the scalar curvature. Okay. All right. So why do we define them? Well, as I was saying, that they have basically the same kind of information as the Riemann tensor, right? So they still capture some of the curvature of the spacetime, but not all of them, and they are easier to work with, and they can have some nice properties on their own. This, for example, it's just a scalar function that has information about the curvature, and you can imagine that, especially in low-dimensional spaces. So, for example, if you consider a two-dimensional space, so let's take a two-sphere, right? Intuitively, you can imagine that a two-sphere is defined entirely in terms of one number, which is its radius. Uh, and this radius must dictate how curved the two-sphere is. If it's a very small sphere, then it's very curved. If it's a very large sphere, then it's locally almost flat, right? Um, and the sphere is defined by, again, one number, just the radius. So it makes perfect sense that you don't need the full Riemann tensor to capture this one number. One single scalar should suffice. And indeed, that is the case. A two-sphere has a constant scalar curvature, and this is basically the only independent component in its Riemann tensor as well. So especially if you're working with low-dimensional spaces, these are very useful tensors to work with. Now, so one consequence of these properties that we have derived for the Riemann tensor is that we can derive some equation for these tensors as well. So notice that, so one of the equations for the Riemann tensor, it involves a covariant derivative. So let's see what the covariant derivative of these simpler tensors are. So basically, you start with this equation, and then you contract these two indices. So what you find is the following. So you find this. So this index is contracted, and when this index is contracted with something in between, we just get the Ricci tensor, right? So now multiply this with G nu sigma. Then you find that, so if you multiply this, then you're contracting these two indices, right? And here you're contracting nu with sigma, and here you're contracting this, which will simply give you the scalar curvature. Altogether, you find the following. These two are the same term, basically. you have two indices contracted and one free index, which is rho. So in other words, you can write so you can define this tensor um, which is always going to be basically divergenceless. If you take any covariant derivative and contract one of the indices, it's going to vanish. And it is, you can also show that it is symmetric in these two indices. And this is called the Einstein tensor. All right. So we are not actually going to do anything with this tensor at the moment, but later when you study Einstein's field equations, you will see that this tensor will appear, which is why I'm defining it right now. All right. So actually, I am not going to say anything more about how to define dynamics using these curvature tensors. So far, I have just defined what these curvature tensors are, and then I'm going to say something about some physical implications. I mean, so far we have talked a lot about basically math, right? We have just done some differential geometry. We have defined how to parallel transport things, how to define geodesics, how to define straightest paths, and how to define Riemann curvature tensor. So these are all useful for general relativity, but so far we have not really said anything about general relativity. We have only talked about the geometry of the thing. So I would like to, so in the remaining part of today's lecture, I would like to say something about what kind of interesting physics we can already see from here. But before I do that, so let's see if there are some questions. There appears to be, again, several questions. So we don't need metric to, okay, I think we already answered that. So do this Lie bracket come from Lie algebra? Is this a coincidence or there is a deeper reason behind that? It's not a coincidence at all. So given a set of vector fields that are closed under this Lie bracket that I have defined, um, this Lie bracket, so you can show that they basically define a Lie algebra where the Lie bracket will be exactly this Lie bracket. So the Lie bracket in both cases refer to the same thing. It's the bracket of a Lie algebra. So a set of vector fields that are closed under this bracket form a Lie algebra. Yes, Lie brackets follow similar properties of, yes, exactly. Lie bracket is part of the definition of an Lie algebra. That's right. So what is that question supposed to mean? Wait, what? Which question? So I think really the source of this question is that when you study Lie algebra, there is a Lie bracket, which is defined in a certain way. And here I am defining something like this as the Lie, and I'm calling this Lie bracket even though I haven't said anything about Lie algebra. So it's a natural question to ask whether this Lie bracket has something to do with the Lie bracket of Lie algebra. The answer is yes, they're exactly the same because these vector fields under this bracket will form a Lie algebra, and this will be a Lie bracket in the usual Lie algebra sense, meaning that this will satisfy the Jacobi identity. An algebra is stronger structure than a vector space. You turn a vector space into an algebra by defining a product or proportion between two elements. Yes, yes. The product proportion is exactly the Lie bracket. That's right. The Taylor function is just a trace. What does that physically mean? Right. So the trace itself, I mean, I don't know whether the trace itself has any particularly significant physical meaning. What I would say is that um, this Ricci tensor, for example, it has d square components, and this R is simply a single scalar. So all we have been doing in this definition is that we are kind of unrefining things. So here we have a lot of independent components containing a lot of information about your manifold. So here we are defining something that's simpler by taking a trace. We're saying that, okay, we don't need to remember all of this information. Let's keep some of them and see what we can infer from that. This is an even further simplification where we're saying, okay, we don't even need these G square components. Let's just keep one component and see if that has any interesting properties. That's it. I mean, if you are on a high dimensional, highly non-trivial manifold, then this single scalar will have very small amount of information about the manifold, right? You will not be able to tell much about that manifold knowing this. You will have to know the full Riemann tensor. But if you are working on a manifold that is much simpler, it has many symmetries, um, then you will often find that, okay, you don't need as much information as the Riemann tensor to talk about that manifold. You can use simpler things such as the Ricci tensor or the scalar curvature. Um, Last question. So any Lie group Lie algebra has a manifold structure. That is also true. Yes. And yeah, there's a very nice story. So you can have a Lie group which is a manifold, and then the group will have a natural action by itself, and those actions will be generated by some vector fields, and those vector fields will then satisfy the same Lie algebra with respect to this Lie bracket. Yeah, everything ties up. Nothing is random. All right. So now, as I was saying, that so far we have talked a lot about geometry, but now let's talk a little bit about physics. Um, so in particular, um, okay. So what we would like to study is redshifts caused by gravity. But let me start with something that has absolutely nothing to do with gravity. Just the Doppler effect. And I expect all of you have seen this in your special relativity class. Um, but it's good to remind ourselves of the notations at least. Okay, because just as a reminder, this has nothing to do with gravity, non-gravitational. Okay. Um, so what is a Doppler effect? So we all know that if you have a light source and an observer of that light who have some relative velocity, then the frequency of the light emitted at the source is different from the frequency or the wavelength of the light observed by the observer, right? So let's derive the formula. Um, so the situation is as follows. So suppose we have a source of some light. So it's a source. And then at some distance, we have an observer. Um, and so this source emits some light, which is then received by this observer, okay? And so let's look at one full period of emission. So okay, I think it's up to here. Okay. So let's focus on this part. So one complete period. All right. Um, so suppose the frequency at source, I'm going to write it new s. Yeah. Suppose it's new s. Um, and so from here, you can compute the wavelength, for example, which is going to be given by c over frequency, right? All right. Um, and so the frequency, mm, okay, so suppose the source is measuring the time it takes for it to emit a full period of oscillation, right? So what is the time? Um, Time measured at source to emit a full period. It's simply, okay, let's call it delta S. It's the inverse of the frequency, right? Um, now, so here we have to be careful because we want to say that when this observer receives this light emission, it is moving away from the source at some velocity, let's say v. Okay. Um, and if that is the case, then this time, which is measured by the source, will be perceived by the observer. So this is our observer as slightly time dilated, right? So time measured at observer to receive a full period. It's going to be um, let me call it delta O. So you're going to multiply it by this relativistic factor, so recall that this factor is just 1 over square root of 1 minus v squared over c squared, right? All right. So this is the time that was measured at source to emit a full wavelength. And this is the time that the observer measured between receiving these two endpoints of a full wavelength. But because of this velocity, during this time, the observer also moves away a little bit, right? So the observer moves away by let's see. The velocity is v, so in this time, and by this I mean in this time, the observer moves away by velocity times this time. Okay. Let me change this notation slightly. I will explain why. Let me call it T0. Um, then, so we can conclude that the time it takes for the observer so delta zero was what I wrote here, but by this T0 I will mean something slightly different. Okay. Um, so it's basically so imagine a situation where you have a source where the source signals the beginning and the end of emission of a full period, which was measured at the source to be 1 over nu s. And the same period, because of time dilation, will be measured by the observer to be something like this, where it's the same, but you multiply by this relativistic factor. And so during this time, the observer moves slightly away from the source, and it moves by the amount velocity times, so whatever this time is, right? Um, so then, so the total time the light has to travel uh, to go from one end of your, so to go from one wavefront to the next wavefront is Now it's delta O. It's going to be TO plus. So it's basically, it would be this if it weren't for the fact that the observer moves away a little bit. So light has to travel a little bit farther, and light is traveling with the velocity c. So in order to traverse this extra distance, light takes a little bit longer, which is this extra time. So it's t0 plus this additional time because the observer moved away a little bit. So you can simplify this. All right. Now, for simplicity, let us assume that the velocity at which the observer is moving when it is receiving the light signal is much smaller than the velocity of light. Okay, this is not a necessary assumption for what we're going to discuss, but it makes life a lot simpler. So then, what you can do is that so you can expand this one over 1 - v over c as a power series, right? So what you find is the numerator, and then you expand the denominator as a power series. So it will look like v over c plus v squared over c squared plus dot dot dot. Well, actually, this is not an approximation. This is exactly equal if I keep the full power series. But if I assume that v is much smaller than c, then I can ignore all of these higher order terms because they're very, very small. So here I'm assuming that v is much smaller than c. So it's just the square, right? So that gets rid of the square root, and you have 1 plus v over c, 1 over nu s. Okay. Um, okay, so what can we infer from here? So the wavelength, as observed by the observer, is c times delta t, the time it took for the observer to receive a full wavelength, right? Times the velocity of light. And then we have already computed delta t, sorry, delta O. So you basically find 1 plus v over c delta s, where delta s is the wavelength measured at the source. So here you can see what the Doppler effect does. It says that if light is being emitted at a source at a wavelength lambda s, and an observer at the time when it is receiving the signal moving away from the source at a velocity v, then the wavelength perceived by the observer is slightly larger than the original wavelength. It is larger by a factor of v over c. So if v is very small relative to c, this factor is quite small. So it gets dilated slightly. So the wavelength becomes slightly larger, which is why it's called a redshift, right? Because red light has the highest wavelength in the visible spectrum. Okay, so this formula, I assume that you already knew. So just keep in mind what it says, that an observer moving away from source at the time of receiving the signal, the velocity v experiences a redshift, right? And this redshift is given by this. So people usually define a quantitative measure of redshift, which is by which fraction the wavelength changes. And as we can already see from this formula, the fraction is simply v over c. So quantitatively, people usually write this fraction with z. It is defined as lambda observed minus lambda at source divided by lambda at source, which in this case is just v over c. All right? Okay. So by redshift, we will refer to this number. This velocity is this velocity. And the important fact here is that the two things only have to be in relative motion at the time of receiving the signal. Okay. Because where is my picture? Yeah. So suppose it was moving away before, but when this wavelength arrived at the observer became stationary all of a sudden. Well, then this wavelength does not get dilated because the time it takes for the observer to receive this wavelength is the same as the time it took for the source to emit this wavelength. The observer did not move away, and thereby creating an extra distance. So there is no Doppler effect in that case. And similarly, if after receiving this wavelength, if the observer starts moving, then the observed wavelength of this particular oscillation of the light is the same as the oscillation here. Right? So the point that I'm trying to get across is that the Doppler effect is an instantaneous effect. The two objects have to be in relative motion at the time of the observation. It doesn't matter whether it was moving before or after. Okay. So as we were saying earlier, this has nothing to do with gravity. It's just about relative motion. But now let us look at gravitational redshift. This is going to be more interesting. And we will very briefly touch upon the subtleties of these things. And I expect you will want to know in more detail what's going on. So you can also find these in textbooks. So for example, you can find this in Carroll section 2.1. So you can look at the details later on. So this is actually a very nice thought experiment. So first, let's assume that there is no gravity, but there is, let's say, so let's think about Einstein's thought experiments of an elevator in free fall, or rather an elevator that's accelerating at a constant rate. So this is going to be our elevator. And let's say it is accelerating with g, constant acceleration. Okay. And suppose there are two observers. One at the bottom of the elevator and another one top of the elevator. Okay. Now suppose this observer emits a light. Okay. And this light is observed by this observer. So okay, so let us also assume some other things. So for example, we consider that this distance is L. All right. Now, at the time of the emission of that light, suppose we are looking at this whole situation from an inertial reference frame, which has the same velocity as this elevator at that time, at the emission of this light. Okay, so when the light is being emitted with respect to an inertial observer, this whole thing is at rest. Very well. But what happens a bit later when that light reaches the ceiling? Your initial reference frame is not accelerating, right? It is stationary. But this elevator is accelerating. So its velocity is going to change. So by the time light reaches the ceiling, this elevator, or rather this observer, will have gained some extra velocity due to the acceleration, right? Okay. So what's going on is that by the time light reaches the ceiling, the ceiling has gained an additional velocity of, so how much velocity is has it gained? So you have to multiply the acceleration by the time it took, right? So how much time does it take for light to travel distance L? It's just L over C. So it has gained a velocity of this much. So what is the situation? So notice that, so from the perspective of a truly inertial frame, so what's going on is that when light is being emitted, so the light is still at the source, um, both the ceiling and the source are stationary because we matched the velocity of our initial frame with the velocity of the elevator at the initial time. But when that light is observed by the observer is moving at a velocity given by this, right? So without knowing anything else, you can apply this formula, because what this formula tells you is that if there is a relative velocity between the source and the observer, then there is a redshift by this amount. And here, there is a relative velocity between the source and the observer. And it's not because the observer is moving away from the source, but because the observer is accelerating. So that when you say that there's a relative velocity between the source and the observer, what you really mean is that there's a relative velocity between the source at the emission of the light and the observer when the observer is observing the light. And there comes the relative velocity, because um, the light is observed after a time L over C, and in this time, the observer has gained a velocity by this amount. So you can simply say that there is going to be a redshift when this observer measures the wavelength or the frequency of the light, and the redshift is going to be given by this formula where V is simply this. Implies redshift by the amount GL over C over another C. So you just have a C squared. Okay. So this is the redshift observed by this observer when this whole setup is accelerating at a constant acceleration g. Okay. So we have said gravitational redshift, but we have said nothing about gravity. We have simply said that you have an elevator that's accelerating at some fixed acceleration. So what does this have to do with gravity? So at this point, you have to remember the Einstein's equivalence principle. So recall that Einstein had postulated that there is no distinction between an accelerating frame and a frame in a gravitational field. In other words, if you were one of these people who were at the top or inside the elevator that's moving at a constant acceleration g, to you, this would feel exactly as if you were on Earth. So this is Earth. And this was a stationary room. Right? So there is no distinction between this situation and this situation. Both will feel identical to these people. And Einstein's equivalence principle was that there is really no difference between these things. It's not just that they feel identical, they are identical. meaning that there should be no experiment that you can perform that would distinguish between these two situations. In particular, if there is a redshift in this setup, there will be a redshift in this setup. So on Earth, if light is emitted from the surface of the Earth and observed by someone at a height of L, they will observe a wavelength that is larger by this fraction relative to the original wavelength, which is quite an astounding conclusion from the equivalence principle, right? I mean, if you have just come up with this thought experiment, you would have to be very bold to conclude that, yes, if you actually do an experiment on Earth, you will observe a redshift, even though nothing is moving at any velocity whatsoever. So the redshift is being caused purely by gravity, because, again, gravity is nothing but acceleration. And in fact, this was indeed observed experimentally in 1959. So there was some experiment conducted in 1959 that sent a bunch of light signals at different heights, and they observed precisely this amount of redshift. Okay, so that is an amazing result. However, again, so notice that this result only relies upon the equivalence principle. It doesn't rely on any more detail of your theory of gravitation. So what that means is that you will observe this redshift in any theory of gravity that is consistent with the equivalence principle. And there can be, and in fact, there are multiple theories of gravity consistent with the equivalence principle that differ in some other detail. And this experiment doesn't tell you which one is right? It only tells you that the equivalence principle is right. All right. So this is called gravitational redshift. There is yet another kind of redshift, which is called cosmological redshift. Let's see. We don't have a lot of time to discuss this, so I will be brief. But again, for details, you can look at, for example, where is it? Eight point five. Okay. This is very interesting. So even if I don't get to explain everything, so let me say something about this setup. So here, imagine that we are in a space-time that has this metric. Okay. Let's look a bit carefully at the metric itself. Apart from this term, the rest is extremely simple. It's just completely flat Euclidean or Minkowski, except for this term. But even with this term, if you look at the space part, so if you look at this part at a fixed time, it's just flat R3. So the effect of this is what? So suppose in flat R3, you have 2 points located at X, Y, Z, and X prime, Y prime, Z prime. So what is the distance between these two things? You would measure this distance as follows. So the distance is going to be given by X minus X prime square, Y minus Y prime square, plus Z minus Z prime square, and the square root, right? So this would be the usual Euclidean distance. Mhm. But now you have this multiplying the metric. So you will simply gain a factor of this in front of your distance if you measure the distance at time t. Right? That's all it does. But what it means is that between the same 2 points, if you measure the distance, that distance is going to change depending on what this value is, right? So at different times, this will have different value, and so those two same points will have different distances. So this is kind of like a toy model of a universe where things are perhaps getting apart, right? Maybe AT is monotonically increasing with time. So the higher the time, the bigger AT. So the distance gets larger and larger by a factor of AT. Uh, right. So I mean, we are saying, I mean, in the inflationary model of cosmology, we said that after Big Bang, space started expanding. So what does that really mean? So this is kind of a toy model of that. So it's basically the distance between the same points is changed as time evolves. Okay. Uh, Now, so what we want to gain from this geometry is that we want to observe some light ray that is traveling through space at different times and see whether we observe the same wavelength at different times for the same light ray. Okay. So what does this computation entail? So if light is moving through your space-time, so it is moving along a null geodesic, right? Uh, um, so suppose this is our null geodesic light ray uh, world line. So this is the line uh, through space and time, and this is going to be a null geodesic. And suppose this is intersected by another geodesic, which can be the word line of an observer, observer word line. Actually, it doesn't even have to be geodesic, right? An observer can be moving. Maybe you're in a rocket or something. Um, so notice that this observer and this light ray, they intersect at some point in space-time. So at some time, somewhere in space, these two things were at the same place. So at this point, this observer could measure the frequency of this light. So what would this observer find? So in order to calculate that, you need to compute the tangent to this geodesic and the tangent to this world line. Okay. So let's say that this tangent I'm going to call it u, and this tangent I'm going to call lambda. Then the energy of the light measured by observer is simply the inner product of these two things, where this is no, has unit norm. All right. So where does this formula come from? Um, so notice that if you have a geodesic, a null geodesic in particular, and if you compute the tangent to the null geodesic, that simply gives you the four momentum associated to this light ray. And this gives you the four momentum associated to the observer, but it's normalized to one. And recall again from the special relativity class that the first component of the four momentum is the energy, right? It's the energy momentum for vector. So in the rest frame of U, if U is normalized, um, and if your matrix starts with something like dt squared plus dot dot dot, then this U is going to look like 1, 0, 0, 0. And your energy momentum for vector is going to look like energy, and then, okay, momentum P1, P2, P3. Okay. But we only want to compute the energy. And if you take this inner product, since these are zero, these things don't matter. You simply take 1 times E, which is E, right? So from here, you find that this simply gives you E, which is the energy of the light ray. All right, so that's the origin of this formula. Okay, so then in order to do the experiment that I mentioned, that suppose there is some light traveling through this space-time, and we want to measure the frequency of that light at different times. What we need to do is that first we need to find this null geodesic, the path that is traveled by a line. Well, actually, we don't really need to find the geodesic, but we need to be able to find this tangent to the geodesic, right? The energy momentum for vector at different times, or at any time, really. And then we just need to look at the first component of this tangent vector at different times and see whether we get the same energy or not, right? Um, and unfortunately, I don't really have the time to show you the computation that leads you from this metric to the geodesic equations. So I will have to skip a bunch of steps. Let me see how much I can tell you. Yeah, so I don't basically have time for any computation, so let me tell you what the steps are. So first, compute Christoffel symbols. Christoffel symbols from the metric. Then look at geodesic equations. So ideally, you would like to solve them, but that is actually too much work because, as I was saying, I don't really need to know the actual geodesic. All I need to know is what the tangent vectors at any time is, right? So recall that the geodesic equation is a second order differential equation in terms of the variables that define either line. But we only need to solve for the first derivative, basically. We don't actually need to know what x is. I mean, so roughly speaking, your geodesic equation is going to look something like this. D lambda square plus a bunch of complicated things involving the Christoffel symbols equals to 0. Now, we don't actually need to solve this thing. We simply need to be able to compute what dx mu d lambda is at some arbitrary value of lambda arbitrary. Um, and if we don't even actually have to compute this for all of the components, I mean, all of the coordinates. So there are 4 coordinates, right? T, X, Y, and Z. Again, so we only care about the energy component. So these other things, so this is dx d lambda. This is dy d lambda, and so on. We don't care. We only need dt d lambda. So basically what you have to do is compute dt d lambda. And there are various tricks that you can use to make this computation easier. At the end of the day, what you will find is dt d lambda is going to be equal to some constant divided by a t lambda. Okay, so this is interesting because this value of constant we can also compute, but it will not be important for what I'm going to say, so I'm not going to specify the value. So what you're going to end up with is the following. So suppose you evaluate, so recall that lambda is the parameter along this line, right? So suppose this point corresponds to lambda equals to lambda 1, and this point corresponds to lambda equals to lambda 2. And what we have computed here is this energy at these 2 different times. So at lambda 1, you have energy E1, and this is going to be given by omega over A T lambda 1. E2 is omega over A T lambda 2. Um, hmm. Unfortunately, I shouldn't have used lambda because lambda is usually reserved for the wavelength. Okay, so let me use something else for the wavelength. Actually, I'm just going to write wavelength. So wavelength measured at 1 is equal to, recall, it's h bar c divided by E1. And similarly, wavelength measured at time 2 is h bar c divided by energy measured at time 2. Um, so if I now compute the redshift, which is, so suppose that the light source was emitted at time 1 and observed at time 2, right? So suppose this is the entirety of the null geodesic. So here the light source was created and here it was observed. So then the redshift is wavelength 2 minus wavelength 1 divided by wavelength 1. So if you substitute for these things, these expressions, and for E1 and E2, these expressions, what you will find is that this is equals to A T lambda 2 divided by A T lambda 1 minus 1. All right, so this is a great formula. So what it tells you is that if A is different, right? So T lambda 2 is in the future of T lambda 1. And if this A is larger in the future, then this is greater than 1 and this is positive. So in a universe where this scale multiplying your spatial dimensions increases with respect to time, then a light source emitted at a time and observed at a future time will be redshifted. Okay, so in an expanding universe, the later you observe a light source, the redder that light will look like, right? So suppose at some time some gamma ray was emitted from some source, but then someone observed that gamma ray at a much later time in a universe that is expanding, um, and maybe they will observe it as a visible light or even radio frequency. And in fact, so one hypothesis of the inflationary cosmology is that so during Big Bang, a lot of very high energy radiation was emitted. But by now, since the space has been expanding since then, so those high frequency radiation, they have redshifted down to some very large wavelengths radio frequencies, which we now know as the what is it called? Cosmic microwave background. So it has now become microwave radiation. Okay. So this is a very nice property. So now one very important distinction between this redshift and the other redshifts and the Doppler effect particularly is that, so for the Doppler effect to happen, the observer has to have a relative velocity with respect to the source at the time of observation. But here, no such thing is necessary. So suppose light has been emitted at some time, then the universe expands for a while, and then it stops. It doesn't expand anymore. And after the universe has stopped expanding, an observer observes that light. They will still observe a redshifted light because what I mean by the universe stop uh, expanding is that, so suppose you plot your AT, right? So let's say this is the time, and here you're plotting AT. So suppose that for a long time, nothing happened. There was no expansion. Then at some point, the universe suddenly started expanding. Uh, so it expanded, so the scale increased, and then it stopped at some other time. And then it stayed flat, so no more expansion. Now suppose that some light was emitted at this time and observed at this time. So the value of AT is still different. It's something here and something else here. Right? It's something here and something else here. So there will still be a redshift because these values are different. So even though nothing is moving anymore. Okay, so this is called cosmological redshift. I mean, so these are all redshifts, but they have different explanations. And so this explanation requires you to actually solve the geodesic equation that we defined in our last lecture, which is why I wanted to mention this. And if we had time, we could actually show you how to solve the difference equation, but maybe you can do it in an exercise. So I will basically stop here. Let me just mention something, which is that so far I have not said anything about the dynamics of space-time as dictated by Einstein. So what I mean by that is that uh, this metric gives you some evolution of space, right? It tells you that there is some flat space at some time, and this flat space keeps stretching and stretching as you move in time. So this is time, this is flat space. So by putting all of these things together, you have a particular kind of space-time. But is this space-time, I mean, does this space-time describe the evolution of space that's in accordance with what Einstein described in his theory of general relativity? The answer is no. This is not a valid spacetime as per Einstein's relativity, general relativity. Uh, so what I mean by that is that uh, recall Newton's equations, right? So what does Newton say? Newton said that d square x dt square equals to force. Well, and if you solve this, you find some line that's the word line, that's the line that a particle follows as it is being pushed by force. Well, you could draw some other lines, right? It's a line, but it's not a line that's described by Newton's equation. Similarly, Einstein's equation describes some spacetime, and this is a spacetime, but it's not the kind of spacetime that is the solution of Einstein's equations. So we still have not said anything about the dynamics of general relativity. We have simply defined some geometry and pointed out that some very interesting things can be extracted simply from the geometry. And so the next thing to consider would be that you study the kind of evolution described by Einstein's equations. And then you see what kind of interesting properties those geometries have that are actually solutions of Einstein's equations and describe the physical world. Okay. So that would be the end. But before I stop, let me mention some important things that I haven't talked about. So in important omissions. Normal coordinates. So these are some special kind of coordinates that are particularly easier to do computations in because you can basically set all of the Christopher symbols to zero at a particular point. So if you want to do some local computations, this is a very nice set of coordinates. And then geodesic deviation. Um, so what this is about is that, so suppose, so we have been saying so far that if something is freely falling, they do not notice any gravity. This is almost true, but suppose this is ours, right? And two things are falling freely. Well, they may not immediately notice any effect of gravity, but they will eventually observe that the distance between them is shrinking. So at some point, they will kind of figure out that something is going on. They're not just really staying parallel. And this will seem to them like kind of a force that they are being attracted to each other. And this is called the tidal force. And that has to do with the fact that these geodesics are not parallel. So this is called geodesic deviation or tidal force. And another thing is symmetry of spacetime. So maybe your spacetime has some rotational symmetry or translation symmetry, et cetera, et cetera. And so here you would study things like Killing vectors and these Lie brackets that we talked about. Um, and this becomes especially important if you want to study, let's say, quantum field theory coupled to gravity, because then you'd have to figure out what kind of symmetry your theory has. Um, so these are all important topics, but slightly away from the core of relativity or geometry. So we didn't prioritize them. But okay, again, maybe you will see some of them in exercises or in tutorial sessions. Okay, so I will stop now. And from the next lecture, you will study, I think, the dynamics, in other words, Einstein's field equations, and okay, maybe other things as well. So now I will answer some of the questions that I can see in chat. If photons travel along null geodesics, in this case, how redshift is affected by spacetime curvature between source and observer. Um, well, okay, so the answer is really here, right? Basically, the energy of the photon as observed by two different observers at two different times is different because space has been stretched. And yeah, you really have to follow the computation to see that the energy is observed differently. Are there any implications works for taking ansatz as A equals X comma T or A equals AX? Yeah, that may be very interesting indeed. But you have to figure out what happens if you modify A. Yeah, if the scale varies with respect to not this time, but also with respect to some of the spatial coordinates, interesting things can happen. So how this AT is affected by the dark energy since the expansion of the universe is way more than what we observe. Well, so the actual universe is not really described by this metric. Um, where's the metric? Yeah. So as I was saying, that this is kind of an extremely elementary toy model, which is not even a solution of Einstein's equations. So this doesn't really have any direct effect. But you will see something analogous if in the cosmology section of this course you study inflation. I think you will see a lot more of this. AT is basically the radius of the universe, something like that, yes. How come? So if you're referring to why this is analogous to the radius of the universe, so imagine that you have your space time is something like three-dimensional, so your space is two-dimensional, and also that the two-dimensional space is like an S2. So then you can imagine that as time grows, the S2 becomes larger and larger. So the radius of S2 increases. So if you mark 2 points on your S2 and if you increase the radius, the distance between those 2 points will increase. Right. So imagine a balloon and you mark 2 points on the balloon, and then if you inflate the balloon, the distance between those 2 points becomes larger. Um, so can you talk about the topic of internship a little bit? Oh, I really don't have time about that right now. CMB. Maybe this is referring to something that I have missed. Right, so the recursion. Okay, I'm not sure what they're referring to. Is there any empirical evidence of the variable speed of light? Not so far, no. In a space-time where the Ricci tensor vanishes, can curvature scalar still be non-zero? No, absolutely not, right? Because so the curvature is the trace of the Ricci tensor. So it's like if you have a matrix and you take the trace. So if the matrix is zero, right, all of the components are zero. If you take the trace, you're adding up a bunch of zeros, so you will end up with zero. We don't observe light comes from the edge of the universe. I'm not sure if this is a reference to something else. Um, but yeah, I mean, maybe the universe has expanded so far that some parts of the universe are now, I mean, so far away that it's not possible for light to travel from there to us. I mean, it has gone outside the light cone. Is Z always greater than zero? What was the redshift? No, it can be negative. So if an observer is moving away from the source, then Z is positive, meaning that the wavelength increases. The observed wavelength is larger than the emitted wavelength. If the observer is moving toward the source, then the effect will be opposite. It will be blue shifted. So the wavelength will decrease and Z will be negative. All right. I think that is the last question. So I will stop here. So this is the end of today's talk officially. So you can, I think, stop recording.
Thank you, Nafis bhai.